Good afternoon, everybody. Welcome to part 2 of Introduction to Machine Learning with Scikit-Learn. My name is David Pugh. I'm a staff scientist at the King Abdullah University of Science and Technology. I'm joined by my colleague, Lyndon Holst, who's here to help answer any questions that we might have as we get started. And so at this point, I've shared all the links that we need to get started with the GitHub repo and the compute resources on the KAUST internal binder hub and the public binder hub. Just before we get going, I want to say a big thank you to our colleagues here at KAUST, Research Computing and IT, who have put together the KAUST Binder Hub for users who are here on the KAUST campus. Just a fantastic resource that I've been using all semester for my teaching, for the Introduction to Data Science Workshop series, and now this Introduction to Machine Learning with Scikit-Learn. And then a thank you to the Binder Hub team, that is maintaining the global Binder Hub, which is allowing participation in these workshops from anyone, anywhere in the world, or here in the Kingdom of Saudi Arabia. So it's just a fantastic resource, and I just want to make sure that I properly thank them and make everybody aware of the great work that they're doing. Okay, so we've got a lot of ground to cover today, so I want to go ahead and just get started. So I'm going to share my screen, and we're going to get rolling. Okay, so here in Jupyter Lab, if you click on notebooks, and then you'll find the two notebooks. So part 1 from last week is last week's notebook. Part 2 is the notebook that we're going to use today. So if you go ahead and double click on the part 2 notebook, then you will find that notebook will load, and then this is what we're gonna be using this notebook for the rest of the day. Okay, so hopefully everybody has been able to find that notebook. Can I just get a quick either check yes in the participants menu, or just let me know in chat that you've been able to find the notebook? Okay, good. Seeing lots of yeses come in. Excellent. Excellent. Okay. Great. I'll just leave that up there. Okay. Okay. Good. Okay, so we're going to pick up where we left off. We're going to continue to follow along with chapter 2 of hands-on machine learning with Scikit-Learn, Keras, and Tensorflow. And that's kind of the chapter on which I have based last week and then this week's workshops. So today we're going to cover preparing the data for machine learning algorithms. And then we're actually going to select and train a number of machine learning models on our data. And then we'll talk about how to fine-tune your model. So by the end of today's workshop, we will have covered everything from getting started and finding data up through tuning a machine learning model and using it to make predictions and assessing those predictions. And so we'll have covered everything in chapter 2, with the exception of the section at the end on deploying machine learning models to production, which is could be a topic for a workshop in and of itself. And given that most of our target audience in these workshops are mostly researchers or students, the deployment aspect is more of a industry commercial aspect that I decided to cut in lieu of, given our time constraints. Okay. And again, so if you're joining late, so the links, I'll send the link around one more time to the main repository. And the repository and the README file has the links to get started with the Koust Binder Hub if you're on Koust, or the public Binder Hub if you're on if you're outside of Koust. Okay. Okay. Right. So preparing the data for machine learning algorithms. So, if you recall where we left off last week, we had loaded the data, and we had done a lot of exploring and visualization of the data, and then we had done a little bit of experimenting with different features and creating some features and things like that. And we had split our data set into training data and testing data using a technique called stratified sampling. And so now, now we're going to kind of pick up there. So this is the training data set that we created last week from using stratified sampling. So if you run these three cells using by hitting by clicking on the cell and then hitting Shift and Enter, or whoops, actually you need to go all the way to the top of the notebook and click on the very first cell and then hit Shift and Enter to actually import the core libraries that we're going to use. And then once you've done that, you can hit Shift and Enter, or there's also this play button up here, but I find that less convenient. Shift and Enter, Shift and Enter. And so this is loading our training data set that we created last week. And then we're looking at the first 5 rows of this training data set. So you recall the features that we have: longitude and latitude. So we've got geographical coordinates, and then the median age of houses, total rooms, total bedrooms, total population, number of households, median income, median house value, and proximity to the ocean. And then the thing that we're trying to predict is going to be the house price, or the median house value column. And then all these other columns are basically features that we have to start with for building a model to predict the median house value. Okay. Okay. So we're going to pick up today with some feature engineering and some data cleaning tasks. We kind of did these last week, but we didn't quite finish them, in part because I wanted to leave them for discussion today. So feature engineering, although we're going to move through feature engineering for this problem quite quickly, in any real problem that you will be working with, I would say the majority of your time will be spent on doing feature engineering. And the reason for this is that the predictive model that you're going to build is in some sense going to be limited by the features that you put into it. So if you put in bad features into a otherwise good machine learning algorithm, you're still going to get bad or mediocre results. So it's hard. You can't squeeze water out of a rock, or you can't no amount of sophisticated machine learning algorithm is really going to save you if you don't have features that are in your input data set that are useful for predicting the thing that you're trying to predict, or for classifying the thing that you're trying to classify. So you will spend a lot of time doing feature engineering for your own projects. In many domains, feature engineering requires a lot of domain knowledge or substantive expertise. And you have to know your problem really well to have a good sense of what things are important for predicting whatever it is that you're trying to predict. So in this case, we're trying to predict housing prices. so somebody who has a lot of domain expertise in housing, in the housing market and housing price dynamics in the United States or in California in particular, would have a significant advantage when it comes to trying to think about what features would be useful for predicting house prices, and maybe how to combine the features that we do have in the data, which are these things here, to come up with other features or additional features or replacement features that would be good for predicting house prices. So I provided a link here to Feature Tools, which I mentioned last week. So Feature Tools is a library that partially automates the feature engineering process, in the sense that it provides a lot of built-in functionality for creating features more features from existing features, avoids a lot of boilerplate code when you're dealing with time series data and you need to create features for time series data. Has some kind of auto ML features that will help automate at least partially the feature engineering process. So it's a good package to be aware of. We're not going to use it today, in part because feature engineering that we're going to do today is going to be fairly basic. It's just easier to get on and deal with it by manually constructing the features. I also want to point out that one of the reasons that deep learning has become so widely used and kind of the state of the art in many problem domains is in large part due to the fact that with deep learning models, you don't hand engineer features. A deep learning model takes raw data, and then with the different layers in your deep neural network, those layers kind of endogenously create the features that are most predictive for the problem at hand. So it kind of automates that feature engineering process, which is one of the most time intensive and expensive in terms of, you usually have to hire people who have domain expertise to help engineer features for most commercial domains. So thus, deep learning, if your problem domain can be well solved by deep learning, you often get this benefit of not having to hand engineer a whole lot of features from your data, and you can kind of just allow the deep learning model to engineer those features for you. And I put a couple of links in here to a very interesting problem or an interesting example of the kind of the benefits in terms of feature engineering of deep learning models. A couple of years ago, there was some astronomers at NERSC in the United States needed to create a machine learning pipeline to solve a classification problem in astronomy. And in particular, the problem was that there was this huge volume of telescope data that was coming in, images of the night sky, of stars and things like this. And astronomers wanted to filter these images and detect interesting things like supernovae that were going on in the data set. And the process that they had historically followed was to get highly trained astronomers to look at all of these telescope images and say, whether or not that there was a supernova in this particular image, and if so, what was the particular type of supernova. And obviously, the volume of data generated by telescopes was enormous and growing, and it was expensive and labor intensive to have highly trained domain experts sit there and look at these images. And so they created a machine learning pipeline called AutoScan. And there's a link here to the paper on arXiv that discusses AutoScan. And AutoScan was a kind of a classical machine learning pipeline using a lot of the techniques that we're going to talk about in the workshop today to automate the process of detecting supernovae from these telescope images. And it was really successful. But a large part of its success was the fact that a large number of highly trained astronomers and domain experts at NERSC created a really rich data set of over 700 hand-engineered features that, because of their knowledge of physics and astronomy and everything else that was involved, they thought would be really useful in classifying supernovas. So the amount of time that was devoted to creating this really rich data set made it very easy for machine learning algorithms to use that data set to detect supernovae. But the hand engineering of features took a lot of time and effort and was very expensive. And then last year, a group of 2 machine learning engineers at a company called DESA, who wanted to learn, basically they were teaching themselves deep learning. And they found this interesting problem, and they developed a deep learning pipeline called Space2Vec. And I've got a link here to the article about this team. And so these 2 machine learning engineers who were teaching themselves deep learning created a deep learning algorithm that operated not on the data set that was created by these NERSC scientists, but on the raw images that were generated by the telescopes themselves. Were able to create a deep learning algorithm that was not only like a little bit more accurate than the autoscan approach developed by the NERSC scientists, but completely eliminated the need for feature engineering entirely, because the deep neural network automatically engineered the features that were required for solving the supernova classification problem. So it's a good example. I mean, this is a particular domain where deep learning is basically a computer vision problem. So it's a domain that is well set up for deep learning. And not all questions or not all problems are attackable by deep learning. And it's certainly true that there's a lot of additional overhead and complexity that often comes with training and deploying large-scale deep learning models relative to the techniques that we're going to talk about today. But I did want to kind of make you aware of kind of the trade-offs on the feature engineering side when it comes to kind of classical or traditional machine learning approaches versus deep learning, so that you can think about when you might want to invest the time in deep learning versus the techniques that we're going to talk about today. Gerard is asking a question. It says semantic segmentation. So I don't believe so. If you're referring to the deep learning model that was used in the Space2Vec algorithm, there's a little bit of discussion of the algorithm in the article itself. I believe that they basically just used a fairly simple convolutional neural network. It wasn't anything. The deep learning algorithm itself was not very sophisticated. Okay. So what we're going to do for feature engineering is also not terribly sophisticated. We're going to take the attributes that we discussed last week, rooms per household, bedrooms per room, population per household, and just create these 3 new features and then add them to our data set. Now, the point that I want to make here is that it's important to encapsulate your feature engineering into a function, because you're going to need to apply this function not only to your training data to engineer the features that are going to be used in training, but then when you go to assess your model on the testing data set, you're also going to need to apply the same function to engineer the new features on the testing data set. So we're going to encapsulate this logic of creating features inside of a function, which I'm just going to call engineer features. And then we're going to call this function on the training data set. And then later, we're going to call the same function on the testing data set to make sure that we do the exact same steps that on the data before we train the models on our training set as we're going to do on the testing data set when we go to predict and evaluate. So again, so shift enter, shift enter, shift enter, and that will load the function into memory, apply the function to the training data set, and then we can look at this training data set with the extra features and see that we have now created these extra features: rooms per household, bedrooms per room, population per household. Okay, cool. So that's all the feature engineering that we're going to do. There's certainly a lot more that you could do with feature engineering. And when we get down to the end and we talk about how well our models have performed, a major way to improve the model performance that we have would be to come back and think clearly and more deeply about the feature engineering that we've done here. Okay, so now we have our data set plus all the features that we want to work with. So now we need to do a little bit of cleaning. So if we looked up here at the top, you remember that we do have some missing values. So total bedrooms is missing a little less than 200 values. And then, of course, any feature that was then created using total bedrooms would also have missing values. And so we'll need to fill in those missing values or drop the observations that have missing values, something like this. There's also, so we'll talk about that in a minute. There were some other issues that we talked about last week, which were that the median house value, which is the variable we're trying to predict, as well as the housing median age and median income, all appeared to be truncated. So if we look at the histograms for these, so definitely housing median age has this huge spike at 52 years. So it seems like the housing data, any house that was older than 52 years seemed to have been just lumped in with 52 years bin. And so we get this huge spike here. Similarly, at 500,000, there is a huge spike in the median house value. So basically any houses that were more expensive than 500,000 were basically just given a value of 500,000. So we need to decide what we want to do. And similarly with median income, I didn't mention this last week, but then I was looking a little more closely. I did notice that median income also has this unusual spike at 15, which would correspond to 150,000 US dollars. So that makes me also think that median income was truncated on the upper end. And so what we're going to do is we're basically going to drop all the training samples that are in one of these bins. So basically, if the training sample has a housing median age of 52, then we're going to drop it. If it has a median income of 15, we're going to drop it. If it has a median house value of 500,000 or greater than 500,000, we're going to drop it. And the idea here is that the reason that we're dropping them is that we want the model to be able to predict house prices that are larger than 500,000. We don't want to artificially truncate the prediction at 500,000. And then similarly, we don't want, since we don't actually know the true values of these housing median ages and median incomes, we don't want the model to kind of learn a relationship that is somewhat spurious, that's only generated because of these artifacts in the data. So we're just going to get rid of all of this. And so that's what this function here does. And again, I'm encapsulating the logic for doing the data cleaning into a function because we're going to have to apply the same cleaning process to the testing data set at the end. So by encapsulating all of this in functions, it makes it easier to reuse them. So this first little function here, drop max values, is basically going to, given a data frame and a particular attribute, it's going to compute the max value for that attribute in the data frame, and then it's going to return a data frame that has only values less than that threshold. So it's kind of dropping any values that are greater than the threshold. Okay. So if we load these functions and then we can clean the data set. And then if we look at the histograms again, you can, if you compare these histograms and these histograms, you'll see that basically these spikes that we have here have now gone away. So now we've done the cleaning. So we did some feature engineering, we did some cleaning. So now what we're going to do is we're going to split our cleaned training data into two data frames. One is just going to be the training features, and then the other is going to be the training target. And the reason that we're going to do that is that we might want to apply different sets of, we're almost surely going to apply different sets of transformations to the training features or the attributes than we will to the target itself. Many times the target is never changed or never transformed. Some cases it makes sense to actually transform the target values, but you almost rarely ever do the same sets of transformations on both features and targets. So we'll go ahead and split them now. Okay. So now at this point, we're ready to deal with missing data. So there are three options that we could at least three options for dealing with missing data. So the first thing is that we could drop any training samples that are missing values for any attribute or feature. So here we'd be basically dropping rows from our data set where there were missing values in any column. So that's one approach, dropping rows. Another approach would be to drop any column that has missing values. And again, depending on your data set, you might want to, dropping rows or dropping columns might drop wildly different amounts of data. If you have a feature that, or a column that has loads and loads of missing values, then maybe dropping that column might make a lot of sense, rather than trying to fill in a lot of missing values. Alternatively, it might make more sense if the missing values are somewhat scattered around, then maybe dropping rows might make most sense. I mean, generally you want to maximize the amount of data that you have. So if you can avoid dropping data at all and follow the third option, which is explicitly decide how to fill in the missing values, that's probably generally the ideal. But if you can't really fill in the values sensibly, then you should decide between 1 and 2, depending on basically which of the two approaches leaves you with the most usable data at the end. So just to kind of show you how you would do this in pandas, so if you wanted to drop rows, then you could follow, you could use the first option here. So basically if you drop, there's a function called drop NA, and then you can put in the columns that you want to consider for dropping rows that have missing values in these particular columns. And there's only one column in our data set that has missing values. So that's total bedrooms. Or actually, no, now this is this would be a mistake, because then anything computed with total bedrooms will also have a missing value. So what were our other, so bedrooms per room will also have some missing values. So we'll need to put, you would also want to put bedrooms per room here. Okay. So this would be dropping rows. So if you run this, you can see that there are now 14,689 rows, and we have dropped rows that had missing values in either total bedrooms or bedrooms per room. And for training option 2, and then note that we have 12 columns, and you can see these are the columns that we have here. So for option 2, now I would also need to go in here and add bedrooms per room. And now you'll see, now we have 14,837. So we have more rows in our data sets and more training observations, but we have 2 fewer columns because we just got rid of total bedrooms and bedrooms per room. So we just don't have those features at all anymore. Now, option 3, which is the one that we're actually going to do, is an example of how you would fill in missing values with the medians. So here, I basically compute the median for total bedrooms, and then I fill the missing values with the fill in a method. And you can provide a Python dictionary where you map values or column names and then the values that you want to use to replace any missing values. So bedrooms per room. So I would need to add bedrooms per room, and then I would need to add median bedrooms per room here. And then I should call this maybe median total bedrooms. If you're not able to follow along with the typing here, then don't worry about it because we're actually going to use Scikit-Learn to do this. But I just wanted to show you that more manually how you might do this. So here I'm basically computing median total bedrooms, and then I need to compute the median for bedrooms per room. And then median bedrooms per room. And then I use the fill in a method to pass in a dictionary that maps the column names with a value that I want to use to fill in A's in that column. Bedrooms per room. Training. Typo. Okay. And so here I have kind of the same number of rows as in the option 2 where I dropped columns. But then of course I have the same number of columns as I had in option 1 where I dropped rows. So basically, if you can fill your missing values sensibly, then that's going to maximize the amount of data that you have for training. So that kind of makes it the ideal approach. So these were examples of how you could use pandas to do all of this. But it's a bit, as you can see, like it's a bit tedious. And there's also issues that these median values here, these values need to be saved, because then when we go to fill missing values in the testing data set, we need to make sure that we use the same missing values that we filled the training set when we fill missing values on the testing set. So that's important because we want to, you want to perform the exact same preparation steps on the testing set as you've performed on the training data set to make sure that your comparisons, when you evaluate your model pipeline with the testing data set, are as rigorous as possible, basically. So if you were going to do this by hand using pandas, you'd have to remember to write or have to store all of these medians, or if you're doing something more complicated, you would have to store any kind of, like, these are called nuisance parameters that you have to estimate that are part of your modeling pipeline, but whose values are not really, they're not trainable, I guess, in any sense. But with Scikit-Learn, we can use built-in functionality of Scikit-Learn to kind of handle this for us. So we don't have to write these down or store the values and remember them to carry them around in our code. So Scikit-Learn has an impute module, and I've provided throughout the notebook, I've provided links to the relevant Scikit-Learn documentation. So there's this model for imputing missing values. And you could go through, this is the documentation for the whole module, and it kind of covers all the major techniques for univariate, multivariate feature imputation, and other things, nearest neighbors, just all the different ways that you can handle kind of imputing missing values in Scikit-Learn. We're going to use a simple imputer, which is basically going to replicate what we did by hand with pandas. So we're going to impute missing values using the median. And so we can create an instance of this simple imputer class where we put the strategy as the median. And so if we execute this cell, we basically created this object simple imputer, which is what we're going to use in a moment to impute the missing values. And so a simple imputer is the first kind of Scikit-Learn transformer that we've encountered. And before we move on, I want to talk a little bit about the rough organization of the Scikit-Learn API, in part because it's important for understanding how to use Scikit-Learn, but also because it's been the design of this API has been very influential on the Python data science and machine learning ecosystem. In particular, Dask and NVIDIA Rapids have drawn heavily from the API design choices in Scikit-Learn. So learning and understanding the key ideas in the Scikit-Learn API will make it easier for you to use these other libraries, Dask, which is for scaling out across multiple nodes in a cluster, and NVIDIA Rapids, which is for accelerating Scikit-Learn workloads on GPUs. So the first kind of key concept is something called an estimator. And an estimator is basically any object that needs to estimate some parameters from a data set. So simple imputer is an estimator because it has to compute, in our case, the median value of columns in a data set. Estimators have a method called fit. And when you call that method with a data set as an argument, or sometimes a data set for features and a column of data for a target, if you're doing supervised learning, then the fit method will estimate any of those, any of the parameters. And like in our case, it basically is estimating the median, but there are other estimators that are machine learning algorithms, and when you call fit, it's actually estimating the parameters of the machine learning algorithm. Many of these estimators have additional parameters that kind of guide the process used in fit when you call the fit method. So those parameters are what are called hyperparameters. Like in our case, the strategy median, the strategy would be considered a hyperparameter of simple imputer. So there are other strategies that you could use here, and you can actually try changing the strategies that you use to do missing value imputation to see if it makes a substantial difference in your overall modeling pipeline. And we'll get to hyperparameter optimization in a little bit. After estimators, then you have transformers. So simple imputer is also a transformer because it can transform a data set into a new data set. And what simple imputer does, of course, is it takes a data set with missing values and then imputes the values using a particular strategy and gives you a new data set that has no missing values. So that's simple imputer as a transform. Many estimators, not all estimators, are also transformers. In addition to, and the way that you perform the transformation is you call the transform method. And usually you have you will call the fit method and then the transform method immediately after, in which case there's a fit transform method which does both in sequence. So in a moment, we'll be using fit and then fit transform with our simple imputer to show how you can fill in the missing values. Finally, there are predictors. And so these are estimators that are capable of making predictions. So they'll have a method called predict, and then it's the method that you use to predict values on a new data set. And we'll see a lot of examples of this. The last thing is that, so Scikit-Learn has invested a lot of time in choosing reasonable defaults for most of the API. So the defaults for the machine learning algorithms for all the hyperparameters are set based on experience from the core developers and the users of Scikit-Learn. So they generally are good and help you get up and running with a sensible baseline system very quickly. So we're going to be using, for the most part, until we get to the tuning section, we're going to be using all default values. Okay, so we created our simple imputer with the median strategy. And now we're going to use it, we're going to fit it with the training data set that we have. And when we fit the training features, we get this error. And the reason that we get the error is that it gives us a good error message. It says, cannot use the median strategy with non-numeric data. So we had this variable, ocean proximity, which is not numeric data. You can't compute the median for non-numeric data. So what will we do? Well, for now, we're actually just going to drop ocean proximity so that I can illustrate how to go through and fit this simple imputer using the median strategy, and then we'll talk about how to deal with this ocean proximity variable. So now, if we basically drop ocean proximity here, and then we just have a data frame of numeric features, we can call our simple imputer. We can fit that to the data, which now computes the medians. And so if you look at the statistics for simple imputer, then these are the median values which are computed on each of the columns in the training data set. So there should be 12 of them. So 3, 6, 9, 10, 11, and then there is the 12th one would have been ocean proximity, which we dropped. So there's 11. And you can compare these to just computing the median with pandas and see that the results are the same, basically. Okay, so now we can use simple imputer as a transformer. So now we've called fit and computed the medians. Now we can call the transform method and transform the numeric features data frame, which has missing values, into a data frame where we filled in the missing values. And then we could just confirm. This is basically asking us whether there are any missing values in this imputed numeric features data frame, and the answer is false. Now we can do the same thing by using the fit transform method and do fit and transform in one go. And that's because, again, simple imputer is a transformer in addition to being an estimator. Okay. So do we have any questions at this point? I've been kind of keeping an eye on the chat, and there hasn't been anything in chat in a while. Does anybody want to ask any clarifying questions or anything before I keep going? So there's a question, so uses only linear fits. So we're not doing, right now, we're not doing fitting any linear or nonlinear models. We're just basically filling missing values by computing the medians. So I'll talk about the difference between linear models and nonlinear models when we get to actually the training section. Okay, so that was basically computing missing values with medians on numeric data. So now let's talk about how to deal with text or categorical attributes like ocean proximity. So for our non-numeric features, we have ocean proximity. And it looks like this text, it's just kind of text data, but actually it's text data that only takes a small number of values. So there's actually only 1, 2, 3, 4, 5 different values in this column. And you know, 1 is an island, there's 1,200 that are near the bay, 1,800 that are near the ocean, and then the rest are kind of roughly evenly split between being within 1 hour of the ocean or being inland. So we need to convert this text data to numbers before we can actually make use of this in machine learning algorithms. So there are a number of ways in the pre-processing module, the Scikit-Learn pre-processing module, for encoding non-numeric attributes or features. So I've provided, again, the links to the Scikit-Learn documentation here. And we're going to talk about ordinal encoding and one-hot encoding today, but there are a few other techniques, a little bit more advanced techniques in Scikit-Learn for accomplishing the same task. So the simplest strategy would be to implement an ordinal encoding, which basically just says, well, instead of using these text representations, we'll just change these to numbers 0, 1, 2, 3, and 4. And so we can do that by creating an instance of the preprocessing.ordinal encoder class, and then ordinal encoder is another transformer. And so we can apply the fit transform method to encode our non-numeric features into an array of numbers between 0 and 4. And the ordinal encoder keeps track of the mapping between the integers and the categories. So you can look at the categories and see that the categories are the same. Okay, now, there's an issue with ordinal encoding that you need to be aware of, and that's if you use, there are many machine learning algorithms will assume that, you know, values in your encoding that are close to one another, that's a meaningful statement to make. So in many cases, if you're doing an ordinal encoding on a text variable where the text variables themselves have some kind of natural ordering, like for example, you know, bad, average, good, or excellent, you could map that to, you know, bad is 0, excellent is 3, and then, you know, good and excellent are closer to one another than bad and excellent, and 3 is closer to 4 than 0 is, so 0, 1, 2, 3. So 2 is closer to 3 than 0 is to 3, and so an ordinal encoding of bad, average, good, or excellent makes sense. Like it's probably a sensible thing to do, but with our well, can anybody basically see an issue with doing an ordinal encoding of our ocean proximity variable? And I may have given away a bit too much at this point, but does anybody want to comment or have an idea about why you might not want to use an ordinal encoding here? So there's a couple of other examples in chat. So days of the week would be another example where there is a natural ordering of days in the week. And so you could encode days of the week as an ordinal encoding. So yeah, so there could be, so there's well, what about, you know, near lake? there's basically a question in chat, well, what about near lake? So near lake would be like an example of a missing category. So you can always have missing categories, but there's nothing you can do, about that. So Michelle has the answer. So the categories are not similar. They can't really be ordered in any sense. So like if we were to, this ordinal encoding basically is giving the value of 0 to within an hour of the ocean, 1 to inland, 2 to island, 3 to near bay, and 4 to near ocean. So first of all, 0 within an hour of the ocean is much closer to 4, which is near ocean in some sense, than it is to any of the others. And so like you're missing that, like that's just a bit wrong. Now you could of course try to say, well, we could just reorder the integers and try to order these more sensibly, and maybe you could do that. But a better approach is to use something called one-hot encoding, which is also called dummy variables in other quantitative fields, where we basically replace one feature with a collection of features, one for each of the categories, and then the values in these new features are either 0 or 1, depending on whether or not a particular training sample is of that particular category. So we're going to create, and maybe this will make more sense when I actually do it. So there's a one-hot encoder class, and we can call the fit transform. We can create an instance of the one-hot encoder and then call the fit transform method to create now a sparse matrix where most of the entries are 0, and then there are 1s sprinkled throughout the rows, depending on whether the training sample comes from within an hour of the ocean, inland, island, near bay, or near ocean. So what you get basically is something that looks like this. So the first 2 training observations are from within an hour of the ocean. The last training observation, an hour of the ocean. The second column is all 0s, and then it has 1s for the rows, the training samples where the category ocean proximity was inland, and then similarly for the other columns. So now we've found an encoding of our category, or our categorical data ocean proximity, that column. And so that's kind of the 2 approaches, the 2 simple approaches, the ordinal encoding or the one-hot encoding. Ordinal encoding is best for categorical data that have some kind of implicit ordering. One-hot encoding is better for categorical data that are effectively unordered, that they don't have any kind of obvious implicit ordering. There's another approach, or one of the downsides of one-hot encoding is that it can create a lot of features. So if you have a categorical variable that has 120 different categories, then you replace that single feature with 120 features, because now you have one feature for each of the categories, each of the values that the category takes. And so you can kind of blow up your feature space very quickly with this kind of one-hot encoding or dummy variable approach. And that might degrade performance for your training of your machine learning models, or it could make some models could become no longer feasible. So the scaling behavior of some models is quite poor as the number of features gets really large. And so as you increase the number of features, then it makes the computational cost of some models prohibitive. And so you won't be able to use some models at all. So if you get into that situation, then you can use an approach called feature learning or representational learning. and it's a bit more advanced than I wanted to cover in this workshop, but it is covered in the later chapters of chapters 13 and 17 of the Hands-on Machine Learning book. It uses some techniques from deep learning. So you have to learn a little bit about deep learning before you can understand how to do this kind of representation or feature learning. But it can be quite a powerful approach. Okay. All right, so now we've looked at how to fill in the missing values for our numerical data, and we've also looked at how to encode our non-numeric values and our using one-hot encoding. The next thing that we need to do is talk about feature scaling. So machine learning algorithms often don't perform terribly well when the numerical attributes have different scales. And the reason for this is that many machine learning algorithms are under the hood are mathematical optimization problems. They set up an optimization problem where you're trying to find the parameter vector that minimizes or maximizes some objective function. And the shape of the objective function will depend on the numeric data that your numeric input data. And if these numeric input data have wildly different scales, then that can distort the shape of the objective function that you're trying to optimize with your machine learning algorithm in a way that makes it more difficult for the algorithms to converge to a local optimal. So the way that we address this is by rescaling our features so that they have the same or similar scales, and to try to reshape the objective function for our machine learning algorithms, so that will be a little bit easier to solve or to minimize or optimize. So just to remember, so if we look at the scales or the ranges, bedrooms ranges from 2 up to 6,210. And then, of course, we've got longitude and latitude over here, which are measured in degrees, and they have much narrower ranges. Median age is measured in years and goes from 1 to 51 now. So you can see there's like wildly different numeric ranges for our data. So again, I'm going to walk through a couple of approaches that you could take. So one is to kind of rescale features so that they all reside within the same range, between 0 and 1, say. So we can do that with a class from the preprocessing module in Scikit-Learn called min-max scalar. And it's, you should see a pattern emerging here with how we use these classes. So we create an instance of the class, and then we call the fit transform method, which takes our numeric features data frame that does not have any missing values, and then rescales it. And by rescaling it, it keeps track of the min and the maxes, because these are going to be this rescaling. We need to rescale the test data using the values from the training data when we go to do that later. So we have to store all of these. And so it keeps track of these things. But it changes the data so that all the values now lie between 0 and 1 for all the columns. So that's probably the easiest to understand. So it basically just takes, so I'll add a, so if we were to then look at the scaled numeric features, the descriptive statistics for that, it doesn't have them because it's not a data frame, it's an array. So if we were to look at the, well, if you just look here, so you can see that all of these numbers are all between 0 and 1. So we basically rescaled longitude, latitude, housing median age, and so forth, so that all the values in the column are rescaled to lie between 0 and 1, and so forth for all the other columns. Okay. But one issue with this min-max scaling is that if you have outliers, so here is a plot of basically just box plots of our of each of the features in our data set. And you can see that there's lots of outliers. There's lots of these values, these black circles, which are outside the kind of interquartile ranges of these distributions. And when you have a lot of outliers, doing a min-max scaling just basically changes, rescales the values of the data so that the horizontal axis would now be between 0 and 1 for each of the features, but you'd still have all these outliers. So it's a feature scaling that doesn't smooth out any outliers that you might have in the data. So an alternative approach to min-max scaling is to use standardization, or rescaling the features so that they all have 0 mean and unit standard deviation. So this is a particularly useful approach if you are going to use machine learning algorithms that often, or that assume that the underlying training data is generated from some kind of Gaussian or normal distribution. Because you're taking, by making this standardization transformation, you're making the variables in your training data set, your features, your attributes, look more normal or look more like they are from a Gaussian process. So if we create an instance of the standard scalar class, and then we can again call the fit transform method, and then fitting the standard scalar computes these mean and standard deviations, or mean and scale parameters, saves those, because again, when we apply this transformation on the testing data set, we want to rescale the testing data set using the means and standard deviations computed on the training data set. Okay. So now we've talked about the 3 big parts of kind of the data cleaning process. We talked about the data preparation process. We talked about the feature engineering, data cleaning, and feature rescaling. So those are the 3 things that you need to do. And you probably have the impression that actually this is quite a lot of work and it's a bit tedious, and this is actually a relatively small data problem. What if I had a lot more features and a lot more, like, wouldn't so it is a bit cumbersome or tedious, but we can actually use a concept in Scikit-Learn called pipelining to create pipelines that will allow us to combine all of these steps that took 50 odd cells in a Jupyter notebook down into a single cell, basically. And that's what we're going to see here. So again, I've made links to the documentation on the pipeline class in Scikit-Learn. So basically, we're going to create 2 pipelines. The first pipeline is going to be for our numeric features. And this pipeline has 2 steps. It has an imputation step, where we use the simple imputer strategy, or a simple imputer with strategy median, and then a standard scalar. So what will happen is that when we fit this pipeline in a minute, for all of the numeric columns or attributes or features in our data set, we are going to impute the missing values with the median, and then we are going to rescale the column so that it has 0 mean and unit standard deviation. For our categorical, we're going to create our categorical variables. We're going to create a categorical pipeline where we create a one-hot encoder, and we process any categorical variables using one-hot encoding. So now we've created these two pipelines, and now we can actually combine these pipelines into a single transformer. So there's a package called Compose in Scikit-Learn, which allows you to compose pipelines together to create a single pipeline. And so we list off our numerical attributes and our categorical attributes, and then we create or use this column transformer class to create a single pipeline that combines our numeric pipeline and the categorical pipeline. And we could have many other pipelines that we wanted to combine. We just kind of put them in this little list. It's a list of tuples. So there's a tuple that has the name of the pipeline, then the actual pipeline object itself, which we created up here, and then the list of the column names for which that pipeline should be applied, which is the numerical attributes here. Okay, so when we execute this cell, we create this pre-processing pipeline object. And this pre-processing pipeline object is a scikit-learn transformer. So it has a fit transform method. So we can just call the fit transform method on the training features. And now this is the raw training features from above. And we get the whole pre-processing features done in one line of code. And this pre-processing features is actually going to be a NumPy array. But we can create a data frame from that NumPy array. We'll use that later. So I went ahead and created it here. And so if you look at these, then so over here now, we don't have ocean proximity anymore, but we have these dummy variables, or these one-hot encoded encoding of the ocean proximity variable. And then these columns here are the 0 mean unit standard deviation rescaled values for the data in those columns. And then just to kind of wrap this section up, I have some links. There's another interesting class for combining pipelines called feature union. It works slightly differently than the column transformer. So I provided the link there so that you're aware of it. It might be useful for you in your work, but I don't want to discuss it anymore today. And then finally, there's this kind of neat little visualization trick where you can configure scikit-learn so that in a notebook, it gives you these kind of nice little graphs summarizing your pipeline. And if you click them, you can see kind of any hyperparameters that you might have set. Like the only one that we've set thus far is median. But if you set non-default hyperparameters, you would see the values set in the constructors here. Okay. So we have been going for almost an hour and a half, and we haven't yet fit a machine learning model. And I guess the fact of the matter is, when you're doing machine learning or data science, like a significant chunk of the work is not actually training the machine learning models. Most of your time is going to be spent on data cleaning, pre-processing, and feature engineering. And then most of the computer's time will be spent training the machine learning models, but that will be a relatively small part, as we'll see, of the actual project, or an actual machine learning project. Okay, so I think now would be a good time to take maybe a short break, like a 5-minute break. So does anyone have any questions about what we have discussed? And if not, we'll take a 5-minute break. Okay, so there's a question about, can we see the box plot after applying the standardization technique? So yes. So I will put that here. So what we want to do is actually, I will copy. So we can just copy that code. Replace that data frame. But we don't want to do the box plot for all of the features, because the box plot for the dummy variable encoded features doesn't make sense. So if we do all the rows, but then we do the, what did I call this? The numerical attributes. So the numerical attributes columns, then I think this should work. Yeah. And you can see, so there's been some reduction in outliers, but you still have, like, total bedrooms has a significant number of outliers here. I mean, so these are now the units of all these variables are the same now. So like, this is a 14 standard deviation observation, which is an enormous outlier. Right? So we'll talk some more at the end about, you know, other things that you might be able to do. Okay, any other questions? Make it 20. So is it prayer time now? I thought prayer time was in like an hour. So there's a question about making it a longer break for prayer. So I'm happy to make it a longer break for prayer. But for some, I did check today and I thought that prayer time was at 3:20. But is now a good time to take a longer break for prayer? Okay, well, let's just go ahead and take a longer break then, because we're about halfway through the day. So now is a good time for a longer break. So let's go ahead and take a 20-minute break, and we'll be back around 10 till. Of course, yeah, different prayer times depending on whether you're in Eastern Province or not. Okay, well, let's go ahead and take a, yeah, so we'll do a 20-minute break and we'll be back at around 10 till 3, okay? Okay, so I'm gonna go ahead and pause the recording now, and I'll see you guys in about 20 minutes, and we'll pick up with actually training some machine learning models. All right, see you in 20 minutes. Okay, so we're back. And so does anybody have any questions before I pick up with training machine learning models? So you've had a little bit of time to, you know, take in some of the material that we've covered in the first half of today. So now would be a good time for questions if anybody has them. No? Okay. Well, let me share my screen and we'll get back to it. Okay. So now we're actually going to start selecting and training models. And again, I just want to reiterate that, as we're going to see, once the data is prepped and ready, training machine learning models is very straightforward, particularly with the well-designed Scikit-Learn API. Training the machine learning models is not your time, not intensive for your time. What requires a lot of your time and effort is actually everything up to training and evaluating the machine learning models. The pre-processing and cleaning and feature engineering, things like that. So here we go. So we're going to get started with linear regression. So the Scikit-Learn has a linear model package, and inside the linear model package, there's a number of different regression algorithms, not just plain linear regression like we're going to use here. There is ridge regression, lasso regression, elastic net regression, a whole bunch of other different models, regression-based models. So let's just go ahead and fit linear regression. So that's it. So we've now fit a linear regression model, and then we can evaluate it using our metric, which was root mean squared error. So that was the metric that we chose for evaluating our machine learning models. So we're going to compute the training root mean squared error. So I should probably put training mean squared error and training root mean squared error in here to reiterate that these are errors. These are the value of our metric computed on the training data set. So these are not computed on the testing data set. But if we compute this, and we see, okay, well, the training root mean squared error, so the units of root mean squared error are US dollars. So our simple default linear regression model has a mean squared error of about a little over $58,000. Now, considering that houses are a few $100,000, like this is a fairly large error in terms of forecasting housing prices, but it's a start. It's a linear regression is typically the first kind of benchmark model that I would fit if I didn't have if there was no other pre-existing numerical solution. So if you remember back to the motivating example that's running through this chapter that we discussed in detail last week, so the current solution in this hypothetical problem is a very manual process where experts on the California housing market sit down and determine what they think a price should be given the economic and demographic information about a census block group. So given that there is no automated prediction algorithm at all in place, linear regression is a very sensible place to start. Okay, but we can do a little better. I guess the other thing I want to say is that the purpose of this workshop, so I'm not going to go into the details of linear regression or decision trees or any of the other machine learning algorithms that I'm going to talk about today. What I want to focus on is the mechanics of using Scikit-Learn to solve a machine learning problem. So I'm going to focus on trying to teach you the API, and then each of the algorithms that are discussed here are covered in quite a lot of detail in further chapters of the hands-on machine learning book. So I would highly recommend, if you want to learn the details, the practical details of these algorithms, that you continue your journey with the hands-on machine learning book, the relevant chapters. Okay, so one of the reasons that linear regression is a sensible place to start, but because it is one of the most simple linear models for your data, it will often underfit data sets where there are more complex or highly nonlinear relationships between the features that you have and the variable that you want to predict, your target. So let's kind of go to the opposite extreme. So if we're going to start with linear regression, then we're going to go and look at a decision tree regressor. So decision trees are a very powerful model, capable of finding very complex nonlinear relationships in the data. So we're going to import the tree package, which is the scikit-learn package where the decision tree regressor class lives. And now we'll go ahead and fit a decision tree. And you can see that the code is between the linear regression and the decision tree regressor. The only thing that actually is changing is the name of the class that we're using to create the regressor. And again, that comes down to this kind of very strongly consistent API that scikit-learn has. So if we fit our our decision tree and then use the decision tree to predict using our training features. So we're going to predict on the training set again and get a measure of the root mean squared error for our training data set. So now we get a root mean squared error of 0. Wow, that's a huge change. Now, you might look at, if you looked at this number uncritically, you might think, wow, well, we're done. This is a fantastic model. We have no prediction error in this decision tree model. But basically, because decision trees are so powerful and flexible, they're also prone for overfitting. So basically what our model has done is it's just massively memorized the entire training data set effectively. And so if we were to use a model like this to try to predict on the test data set, it's unlikely to do very well because it has just memorized the training data set and has no ability to generalize to new data. So Mohammed asks a good question. So do linear regression or decision tree models perform cross-validation automatically? No. So we're going to talk about that. You might see this header for the next section, better evaluation through cross-validation. We're going to talk about how to do exactly that. And these models here are just a straight fit of the models on the training data. There's no cross-validation. So let's talk about cross-validation. So a better way to evaluate models on the training data is to use a process called cross-validation. And basically what we're going to do is we're going to decide to divide up our training data set into some number of folds. So in this case, we're going to use 10. So we're going to divide our data set into our training data into 10 different subsets randomly. Uniformly at random, we're going to create these bins. And then we're going to use 9 of the bins, so 9 of the folds, to train the model. And then we're going to use that trained model to predict the values on the 10th fold. And then we're going to do that 10 more times. So basically, each of the 10 folds is going to have its chance to be the testing data set to evaluate the model's performance when trained on the other 9 folds. And when we do this, then we will get basically 10 estimates of the root mean squared error for our model. And then we can look at the average and the standard deviation of those scores to kind of come up with a much better estimate of how well our model will perform on when it sees new data, basically. So again, there's a link to the cross-val score function in the model selection package, and this explains kind of how it works. You can use many different ways to do the random splitting. If you just provide an integer, which is what we're going to do, it will do uniform random splits into the number of folds that you request. But if you wanted to use some more complicated splitting scheme, you could do that. So we'll put 10 here for our number of folds. And now the in jobs, I'm going to change this to -1. So I had put it at 10 earlier. Basically, when you're doing cross-validation, each of the individual fits for the cross-validation can be done in parallel. So if you have access to a machine that has 10 cores, then you could launch 10 jobs and do the cross-validation for, do a 10-fold cross-validation the same amount of time it takes to do a single estimation of the model. But on the cloud instances, actually, you're not going to have 10 cores. So if you change this to -1, it will take advantage of all the cores that are available. So it will launch 1 job if there's only a single core available, or 2 jobs if there's 2 cores available, and so on and so forth. So if we just set that to -1, and if we, so there, I've run this cell and we're done. And so now I've created this little helper function which just computes the mean and the standard deviation of the root mean squared errors, and we'll use that to display the results for our regression. So now for our machine learning model. So now we've done cross-validation with linear regression, and we get on average a root mean squared error of a little over $58,000, and then a standard deviation of about $2,000. So now let's do the same thing for decision trees. Again, I'm just going to change this to -1. And it's important to change the in jobs to -1 if you're running on the public binder hub. I did run into some out of memory issues if you are on the public binder hub and you set the number of jobs to be too high. So decision tree is done. And again, we can look at the decision tree. And now what do we see? So when we just fit a decision tree to our whole training data set, it just completely overfit the data set and memorized the training data. But now what we get is when we use cross-validation, so when we chunk the data set into 10 different chunks, and we take 9 of those chunks, train a decision tree, and use it to predict on new data that it's not seen, and we do that 10 times and average the results, we get $63,000 as an error. So this is the fact that on the training data set, a decision tree gave us 0 error, but then when we did cross-validation, the average error goes way up. That's a dead indicator. It's a clear indicator that the decision tree was overfitting. It was, when you use cross-validation, you get an estimate of the out-of-sample prediction performance. It goes, if that goes way up relative to fit on the whole training data, then you know that that original result was spurious. In fact, now decision tree is actually worse than the simple linear regression model. It has a much higher, significantly higher average root mean squared error. So what can we do? How can we improve the situation? So let's take a look now at random forests. So random forest regressor takes the decision tree approach, but instead of just fitting a single decision tree, it actually trains a collection of decision trees. So hence the concept of a forest. So it kind of randomly creates a number of different decision trees using subsets of the features from the data, and then fits those small models, and then averages the prediction across all of these decision trees to create an overall prediction. So it's a technique that is called, it's an ensemble modeling technique, where you make a lot of simple models and then you average the predictions from these simple models to get an overall prediction. So it's an example of ensemble learning. There's a whole chapter, again, in the hands-on machine learning book on random forest regression. Very powerful technique, performs well, widely used, or performs well across quite a wide variety of applications. So much so that often random forest is the first place I start for like serious modeling. So with linear regression, I might use that as a benchmark, but I never really think that linear regression is going to be the end of the story. So that's like a point of departure and a benchmark target for my metric. But random forest regression, often I'll end up spending quite a bit of time tuning a random forest regressor to a particular problem, because they do often perform quite well. Okay. So again, we're going to fit our random forest regression. And it takes a little bit longer because, again, it's fitting not a single model, but actually, by default, 100 different decision trees to the data, and then averaging the predictions from those 100 different decision trees to produce an overall result. So now we've trained our random forest regressor. We can compute an estimate of the training root mean squared error, and we get 16,000. So that's much better than linear regression got on the training data set. But of course, we need to do cross-validation to understand how to get a better estimate of how our random forest regressor will perform on new data. So we'll change this to -1 again. And now this is going to take a little bit longer, because not only are we training a much more complex model, but we're doing it CV folds number of times. So we're doing it 10 times. So, and we probably don't have that many cores on our cloud instance. So this might take, probably not quite 10 times longer than just estimating it a single time. There is a, while this is, so Nabil asks, what is a good book for deep learning hands-on? So if you're interested in using TensorFlow, then the book that we're looking at, Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow, is probably one of the best books to get started with TensorFlow. If you're interested in Pytorch, then I'll have to think about what some other good books for Pytorch might be. Is there a specific, question in chat, is there a specific reason why you chose 10 folds? No, not really. What the trade-off in the number, so the default value is 5 for CV. The trade-off that you have is the larger number of folds that you train, kind of the more precise estimate of the out-of-sample performance of your models that you'll get, but then the computation cost goes up as well. Unless you have access to a machine with lots of cores, then you could do, if you had 72 cores, you could do 72-fold cross-validation in the same amount of time it would take to train the model once. But actually, the default value of 5 is pretty good. I'm not sure I had a very good reason for changing away from the default value of 5. Okay, so we've done, but now the code here is completed. So if we look at the cross-validation estimate of our root mean squared error, now we get 44,800. So this is still an improvement, a substantial improvement over linear regression. But notice that it's a big jump up from what we got when we estimated the random forest regressor on the whole training data set. So again, the fact that the cross-validated estimate of our root mean squared error is substantially higher than what we got when we fit the model on the whole training data set is an indication that this model with the default values of hyperparameters is overfitting the training data set. And so we need to think about what we could do to tune the hyperparameters to improve on that situation, to try to constrain the random forest regressor so that it does a better job of generalizing to new data, is what we want to do. Okay. So now what I'd like to do is just to give you a few minutes to actually try this out on your own. So I have given you some links to nearest neighbor and the support vector machine packages in Scikit-Learn. And so I would like you, I forgot to hide the answer cells that I made in the notebook here that have the answers to this, but I've given you the import statement for importing the neighbors package and importing the SVM package. And take a minute and see if you can make the very minimal changes to the code that you need to make from the examples that I've given above for decision trees and linear regression and random forest, and see if you can train a nearest neighbors regressor and a support vector machine regressor, and see how you go, basically, just to get some practice on your own from writing these. Oh, so how do you hide the cell? So if you find so over here, every cell has a little blue just to the left. If you find it, you can click it to toggle it open and close. So you can, click on the one next to the 3 dots is the answer that I hid. So if you want to try to hide it, then you can click on it and hide the answer. So I'll set my timer for 5 minutes and give you guys 5 minutes to take a look at that. See if you can write some of this code on your own. And then obviously I'm happy to take questions. So if anybody wants to ask questions. And if there are no questions, I'll Google about for a good reference for Pytorch for deep learning. Okay. Okay, so I'll put a couple of links that I've found for deep learning with Pytorch. And then for TensorFlow, the best place to get started is the book that I've been using here, the section 2, which covers all of the TensorFlow and Keras. Okay, so there's another good book called Deep Learning for Coders that uses a library called FastAI, which is a higher level kind of API on top of Pytorch, similar in many respects to what Keras does for TensorFlow, but for the Pytorch community. Something else to take a look at. Any other questions? Just have about a minute left. Then we'll go over the exercise answers. So Summer has a question: what is the difference between Pytorch and TensorFlow? So TensorFlow was one of the first frameworks for deep learning that came out. It was developed internally at Google and then open sourced maybe 5 years ago, something like this. It is the most widely used framework for doing deep learning. So TensorFlow, particularly TensorFlow version 2 and Keras, are the most widely used frameworks for deep learning. It has a lot of support. TensorFlow has a lot of support that makes it well suited for industry use cases. So there is a lot of support for things that commercial enterprises need to do to take a deep learning model from start to finish, including deploying it and embedding it in some kind of a web application and serving predictions from the model to solve problems for users. Pytorch came along and addressed many of the early kind of pain points of using TensorFlow, and was developed by Facebook, was open source maybe a little more than 3 years ago now, and has found widespread adoption in academia and research use cases. It's a lot, in some sense, it's more user-friendly. It's easier to change a lot of the internal behavior of the way things work. And so it's like, for example, like CALS, most of our users here at CALS are using Pytorch, in part because they're almost exclusively doing research, building research applications. Pytorch, relative to TensorFlow, Pytorch is a little thin on support for many of the things that are required to deploy deep learning applications in production, but that's changing. So there's a lot of work being done within the Pytorch community for supporting these things a little better. Maybe both of them support automatic differentiation which is what is really required to make training of deep neural networks practical. So computing derivatives automatically. And both support accelerated training on GPUs or TPUs. So both support accelerated hardware. There's even newer frameworks like JAX, which is a new framework coming out of Google's research community, a research group, which is making a lot of noise for being very popular and easy to use. JAX basically has the same API as NumPy. So if you know how to write NumPy code, you can basically use JAX as a replacement for NumPy, and which is, I think, one of the reasons why JAX is getting a lot of recent adoption, because almost everybody in the data science machine learning community knows NumPy really well because it's been around for decades and is just somewhat ubiquitous. Okay, so that's my answer to what's the difference between Pytorch and TensorFlow. And so now let's get back to the answers to our to the question that I asked. Okay, so I wanted you to kind of get a little bit of practice with Scikit-Learn, so fitting a nearest neighbor model. So again, it's basically the same, except you know, we could actually even have cut this out and just said, well, let's call this you know, an estimator, and then written it like this. And then actually you wouldn't need to change, maybe we'll just change this to -1 so we don't get any accidental out of memory errors. But then you wouldn't need to change anything except just the name of the class that you are providing as your estimator. I mean, so it's really easy to swap out models, and that's kind of the point that I wanted to make with these exercises. So here, got to import the neighbors package first. But once you import it, then you can run a k nearest neighbors regression algorithm. And then we can take a look at, with cross-validation, 10-fold cross-validation. And then we can take a look and see. So this is 54,000. So that is, I think, about the same kind that we were getting with linear regression, I think. What was linear regression? So 58, so a little bit better than linear regression, but not as good as the random forest model. And then if we look at the support vector machine, then with the support vector regressor, change this to -1. Oh, again with the imports. We can fit a support vector regressor, and this takes the support vector regression is a model that or an algorithm that doesn't scale particularly well to problems that are either large sample or large features. So for smaller problems, support vector regression, or well, small means basically less than 100,000 observations. You can usually use a support vector regression. But anything larger than that in terms of number of samples, it really will take probably too long to be computationally feasible. But this doesn't take too long. I think it takes like, I tried it earlier, it seemed to take about 3 minutes or so when I did it before. There we go. And so this one appears to do quite a bit worse. But again, so these are all of these models were trained using the default set of hyperparameters. And if you were to look at for example, if we look at support vector regression, so there are there's several different kinds of support vector regression algorithms that you can use. But if you were to just look at the SVR class that we're actually using, there are, 1, 2, 3, 4, 5, 6, 7, 8, 8 or so hyperparameters. And depending on the values of those hyperparameters, you might get wildly different performance for the support vector regressor. So for each of these very flexible models, you need to do a lot of hyperparameter tuning to find a set of hyperparameters that works really well for your data set, for your problem. But to actually understand how to tune these models, you need to understand exactly how the algorithm works. And so this requires a more detailed dive into this book, where you can go through the chapters that cover each of these algorithms in quite a lot of detail. Or, this is the kind of knowledge that you would get from, a theory course on machine learning that you might take at your university. They'll tend to focus more heavily on the theory, the statistical theory, or the computational theory behind the models, behind these kinds of models. But then you need to dig deep into the Scikit-Learn API to understand how, in practical terms, you would tune these algorithms to solve your problem. So just because a very flexible model like support vector regression seems to perform poorly here, it could just be that it needs some tuning, and which leads us to our next section, which is about, well, how do you tune your hyperparameters in Scikit-Learn? So, perhaps unsurprisingly, the most common, when I interact with users and clients, the most common kind of hyperparameter tuning scenario is a lot of just trying different things, a lot of manual, just changing the hyperparameters and rerunning the script and see what answer you get, and change them again and rerun the script and see what answer you get. And this manual approach is very tedious and not very scientific, because unless you're actually keeping track of your hyperparameters that you're trying, the combinations that you're trying, just manually trying different things is unlikely to lead to a good result. So you need a more systematic approach. So I'm going to quickly mention two approaches for doing hyperparameter tuning: grid search and randomized search, which are implemented in Scikit-Learn, and we're going to talk about how to how to write the code to implement these kinds of parameter searches. And then I'm going to talk a little bit about a package called Optuna for doing larger hyperparameter searching using more sophisticated statistical approaches for hyperparameter tuning. Okay, so the simplest approach, which kind of mimics the manual fiddling of hyperparameters, is grid search. So with grid search, you basically create a grid of values for your hyperparameters, and then you search within that grid. Then you manually try every possible combination of hyperparameters and record the result, and then you take the hyperparameters that gave you the best result as your new values of your hyperparameters. And along the way, you're also doing cross-validation. So you're not just fitting to the entire traded dating set once for each set of hyperparameters. You're actually performing cross-validation for each set of hyperparameters, which is what you want. You want a robust, that way, for each set of hyperparameters in your grid, you get an estimate of out-of-sample prediction performance with the cross-validation. And so here we're just going to do 5-fold cross-validation. So instead of 10, I'm going to reduce it to 5, and I'm going to change the in jobs to -1 again. But then the key thing here is the parameter grid. So you can see that actually this looks very similar to the code that we wrote above for the cross-validation score. The difference here is that we have to specify this parameter grid. With our parameter grid, we provide basically a list of dictionaries, either a single dictionary or a list of dictionaries. And in the dictionary, the keys in the dictionaries correspond to specific hyperparameters in the algorithm. So for example, if we wanted to look at, so we're doing random forest here. So we find my random forest regressor. So in the random forest regressor, you can see, so these parameters here are all of the hyperparameters that you can tune. Well, not all of them. So like in jobs, random state is the random seed, in jobs is the number of cores that you want to devote to fitting the random forest regressor. But the rest are hyperparameters. So there's quite a lot of hyperparameters in there, including in estimators, which is the number of decision trees in the forest, basically. So the number of decision trees that you're going to fit. So by default, you're going to fit 100 different decision trees. And so where are we? So we're back down here. So for the number of decision trees, I'm going to try 10 and 100. So 100 is the default value. I like to always include the default value for any parameters that I search over in my grid search CV, because that way I know that I will at least do as well as the default parameter combination. So I'll try 10 estimators or 100 estimators. For max features, so max features is random forest, you choose a random number of features to include in each decision tree. So the max features is the maximum possible number of features that you could include in any particular decision tree. So a smaller number of max features means that your individual decision trees are not going to be as flexible, so they're going to be less prone to overfitting, but then they might underfit. So usually you want to have some kind of balance between, this is a key parameter that you can help reduce your overfitting by this max feature. So the values that I'm trying are auto, which basically sets max features equal to the total number of features. So that's like maximum flexibility. Square root, which takes the square root of the number of features as the max number of features. And then log base 2, which takes the log base 2 of the total number of features as the maximum number of features. Now, again, like you're going to have to really dig into both the API documentation, but also the theory of the different models that you're trying to fit in order to understand how best to tune your hyperparameters for your particular objective. So this is hyperparameter tuning is going to require, especially as you're learning how to approach machine learning problems and you're learning these algorithms, you're going to have to spend a lot of time figuring out which hyperparameters to tune to accomplish the task that you're trying to accomplish. There are 2 different parameter values here to try and 3 different parameter values here to try. So that's 6 parameter combinations. Then we pass in a second dictionary, just as an example. You don't have to pass a second dictionary, but here is an example where I'm passing in a second dictionary, which fixes the value of this bootstrap hyperparameter to be false, and then tries some smaller number of estimators and some smaller numbers of max features, just to show that you can also put an integer in as a max feature. And that gives you 1 times 2 times 3, so 6 more parameter combinations to try. So all in all, there's going to be 12 different combinations of hyperparameters that are going to be fit or tested with this grid search algorithm. And for each combination of hyperparameters, I'm going to perform 5-fold CV to try to estimate the out of out-of-sample prediction for that set of hyperparameters. So we can create this grid search CV. This grid search CV is itself an estimator. So again, we just call the fit method on an estimator. And now you can see on this instance, I have 2 cores. So I can split my so I have 12 candidates for hyperparameters. I'm doing 5-fold. So in total, I'm going to fit 5 times 12 or 60 different 60 models. And I'm going to split these 60 fits across the cores that I have available. So I have 2 cores. So there's basically going to be 30 fits done on each core. Scikit-Learn takes care of making optimal use of my cores. So if I had, a server class machine with, say, 72 cores, this fit would take basically the same amount of time it takes to fit, 1 model. And so this is going to take a little bit less than, a minute and a half to do 60 fits. So now we can look at the grid search CV has a number of different attributes. So once you fit grid search CV, you can look at the best score, which will be the best negative mean squared error. So to convert it into our metric, which is the root mean squared error, we need to reverse the sign and then take the square root. So the root mean squared error is now, for the best grid search, is 44,934. And what did we get for 44,800? So somehow I must not have quite set my default or set it properly to recover the default, because I was expecting to do it. Wow, okay, but there's some randomness involved. So this is basically doing as well as the default hyperparameters. So if we look at actually the best parameters, what we find is that the best number of estimators was 100, but the max features was the square root. So that basically taking the square root reduced the max number of features available for each decision tree, which had a regularizing effect or a reduce the flexibility of the random forest, which makes it more less prone to overfitting, and probably made it perform better on the outer sample prediction, which is the estimate that we were getting with the cross validation. But it's worth noting that the number of estimators here is 100, and we didn't try a value higher than that. So, maybe you might want to go back with this again and try, a higher number than 100 and see, because maybe, maybe we need a larger forest of models to get an even better answer. Let's see what questions we have in chat. So the question in chat is, how big can this grid be? Is there a max number of combinations? So the answer is depends on how much compute you have. So hyperparameter optimization is a very parallelizable task, because, for each set of hyperparameters, it's basically a parallel job. So you can fit all of these jobs in parallel if you have enough cores available. Also, some of the machine learning algorithms themselves are parallelizable, so you can basically the answer is it depends on how much compute you have available and how much time you're willing to wait. So if you're going to run on Google Cloud or on AWS, then the limit is going to be on the amount of compute you can get. If you're just going to use Scikit-Learn, so Scikit-Learn will take advantage of all the cores that you have on your machine or your server. So you'd be limited by the amount of cores in memory that you can get on a server on a VM on, say, Google Cloud or on AWS. But you could, you could combine Scikit-Learn with something like Dask and expand to do hyperparameter search across multiple nodes. Grid search is usually not the most efficient way to go, though. It's very actually inefficient. There are better approaches that we're going to talk about in just a second for hyperparameter tuning, but it's it's an easy way to get started with hyperparameter tuning. So you can get access to the best estimator. So the grid search CV goes through all of these different hyperparameters, and then the best estimator will be the model fit with the best hyperparameters. So you can basically get access to an instance of a random forest regressor, which is trained on your data using the best combination of hyperparameters. Now, when you do hyperparameter tuning, and once you get a model that you're happy with, then you should always save the model to disk. And you do this by a process called serialization. So you basically create a file on disk that is a representation of your model that you can then load later if you need it. And so here we're going to use a library called joblib, and we're basically going to store this entire grid search CV object, which is going to store all of the cross-validation data, all of the scores from cross-validation, all the different parameter values tried, as well as the models trained on those parameters. So basically, it's going to store everything about this whole hyperparameter tuning process into a single file using this joblib.dump function. And we're going to dump it into this file here. And we're going to give it a name, but we're going to stick the timestamp or something to uniquely identify this particular model, so that when we recover it later, we can recover it later, basically. So if I look at in the results directory, there's a models directory which is empty. But if I run this cell, then in a couple of seconds, we should see so here is this, it's called a pickled file, a serialized representation of our model. And we can actually reload it using the joblib model. So you could do joblib.load and then pass the file that you dumped with the joblib.dump function. And then you could reload the model. So you can see this is just to basically show you that you've reloaded the model and you've got the same parameters here and everything like that. But that's really important. So if you're going to invest a lot of computational time in tuning a model, you want to store that model on disk so that you can reload it later. Okay, so that's grid search. A more efficient strategy, if not maybe a little bit more complicated to get started with, is randomized search. And the way randomized search works is that instead of providing a grid of parameter values to try, you provide a probability distribution over for each of the hyperparameters that you want to test. And then the randomized CV will basically randomly sample from the joint distribution of all your hyperparameters and try different values. you can control the way that the sampling is done if you want. If you want to have more sophisticated control, but the random sampling of parameters is a nice introduction to, or a nice point of departure for the more production grade hyperparameter tuning libraries like Optuna, which use sophisticated probabilistic sampling to efficiently sample the hyperparameter space to find good combinations of hyperparameters. So I'm going to import the stats package from SciPy, and then for the number of estimators, I'm going to, so the number of estimators can either be an integer or it can be, no, actually, no, it needs to be an integer. And so I can use this geometric distribution with this particular value of its parameter p to determine the probability with which I will sample different integers, basically. And then so the randomized search will sample from that distribution to find a value for the n estimators. And then it will sample from a beta distribution with these parameters to get a value for the min sample split hyperparameter. And then it will sample from this beta distribution with these parameters in order to get a value for the min samples leaf. So it requires a little bit of thought because you actually have to think about what's the appropriate probability distribution to use for these different hyperparameters, and sometimes that's not obvious. A beta distribution is nice because it's a parameter distribution that allows you to kind of put different kind of shapes of probability, but over the interval 0, 1. So instead of uniform on 0, 1, you can make a probability distribution with a beta distribution that has all kinds of different shapes. And it's a good way it's a good probability distribution to use when your hyperparameter ranges between 0 and 1, basically. And here, the min sample split or the min samples leaf, if you provide a value between 0 and 1, that's basically saying the percentage of, or the fraction of training samples that has to be available in a node in your decision tree before you can either split that node into 2 nodes or that you have to have in a leaf. And these are other parameters that you use to control the amount of flexibility in your decision trees and then in your overall random forest. I'm just going to change this to -1. And with randomized search, it's a little bit easier to control your computational budget because you can set the number of iterations is basically the number of samples from this joint parameter distribution that you're going to make before you stop searching, basically. So, I set this to 10 by default. I'll set this to 20 basically and see how that goes. So we create this randomized search CV, and then we fit it. So I'm going to do 100 different fits because, again, I'm going to try 20 different samples of parameters from this joint distribution, but then I'm going to do 5-fold cross-validation for each of those 20 sets of hyperparameters, which means that I have 5 times 20 or 100 total fits split across some number of cores. And hopefully I haven't picked a number that's going to be annoyingly high. But I'll just go ahead and queue these up for execution when this cell is finished. So while we're waiting, are there any questions about hyperparameter tuning? If not, maybe this would be a good time to talk about Optuna. So Optuna is a library for doing hyperparameter tuning. It's not just for Scikit-Learn. As you can see down here, it basically works for Pytorch, Chainer, Tensorflow, Keras, MXNet, Scikit-Learn, XGBoost, LightGBM. So it can be used to do hyperparameter tuning for a wide range of underlying libraries that you're using for your machine learning models. And it's installed in this Jupyter Lab instance. So if you go back to, to the, in the environment.yaml file, so you can see, so Optuna, I've installed Optuna in here for you. As well as, of course, XGBoost, LightGBM, of course, Scikit-Learn. I didn't install any of the Pytorch or TensorFlow into this environment. But Optuna Optuna, I think, is the best way to go for your hyperparameter optimization. So it's worth your while to invest in learning how to use Optuna. You know, when you find yourself doing hyperparameter tuning, you know, you might try one of these first, but Optuna, because it does a much more sophisticated sampling of a hyperparameter space using more sophisticated probabilistic methods, you're much more likely to find a better set of hyperparameters using Optuna than you will with these, you know, easier to get started but more simpler tools. Okay. So there's a question in chat about what is the difference between batch training and online training? And how do you do that using Scikit-Learn? Okay. So chapter 1 of this book of the hands-on machine learning with Scikit-Learn and TensorFlow is a good reference for all of the different kind of machine learning terms, for example, including batch training and online training. Online training basically means that you have data that's coming in a stream, maybe in real time from users are interacting with your web application, and that's generating data in real time. And that real-time data comes into your model, and your model is retrained kind of as it's, as new data comes in, your model is being retrained. And usually online training is not real-time training, it's more like mini batch training. So, you know, maybe like every hour, you know, a new batch of training data is created and fed into the model, and the model is retrained on that with that new batch of training data, and then makes predictions over the next hour using, you know, everything that it's learned up until the previous hour. And then after the hour, another hour passes, you've accumulated another hour's worth of training data, your model is retrained on that new training data, and so on and so on. Now with online training in Scikit-Learn, the way that you do online training is not so much within Scikit-Learn, because it requires taking a model pipeline that you are training and embedding it into a system where it's getting fed data in near real time. So if you want to learn more about online training, then I would have a read through the section at the end of this chapter 2 in the textbook, which talks about some of the details about deploying an application in a web environment. And then you can see kind of, you'll be able to see better the difference between online training and batch training. Normally, you as a machine learning engineer or data scientist will create the machine learning model and then turn the machine learning model over to a data engineer or somebody else who will then embed that machine learning model in a production environment and then enable the online training in the production environment. Because usually embedding a model in a production environment requires a lot of like web development skills and a lot of data engineering skills, which are related but different than the skills that a machine learning engineer or data scientist might have. Okay, so we're done with randomized search CV. Now, so it took us about 6 minutes to do all 100 of these fits. And if we look at the best score was 45,489. So the default values that we got, what is this? So that's slightly worse than grid search and also slightly worse than the default parameters. So basically, these hyperparameter tunings have not gained that much over the default parameters. And so here you can see the best parameters, and then again, we could dump this to a file. So now if we look in our results file, we have 2 models. Well, 3, because then I reran this one already, so I shouldn't have done that. Just delete this one. So we haven't really done that much better with the hyperparameter tuning. So what do we take away from this? So there are a couple of takeaways from this. So one takeaway is, again, Scikit-Learn from experience has really good default parameters. So actually, to improve on the default parameters for many of these models, you have to know quite a lot about either the algorithm itself and also how the algorithm itself is going to interact with the problem that you're trying to solve. So this is where you have to develop your kind of knowledge and intuition and experience in machine learning, so that you kind of know which hyperparameters to tune and which are the ones that are going to be relevant for your particular problem at hand. So maybe there's probably 24 hyperparameters in the random forest. Maybe there were some other hyperparameters that I should have picked that would have allowed us to get better performance by exploring those values. So there's a question in chat. So if root mean squared error is overfitting, what would be the best root mean squared error? So we're going to talk about that in a minute. But the short answer is that root mean squared errors are going to be a relative measure. So, I mean, 0 indicates that your model has memorized the training data. So that's and not going to generalize well. But, a root mean squared error number can really only be compared to a root mean squared error from another model. So basically, there is no best root mean squared error. There is a better root mean squared error than the current solution, but it's all relative. So you can't take, there's no absolute answer to what is the best root mean squared error. Okay. So we've done parameter tuning. And so now I want to just talk a little bit about how to analyze the things that you should think about in terms of analyzing the models, how to look at errors for models. And then we'll talk about how to make predictions on the test set. Okay, so analyzing best models and their errors. So again, this is actually a very deep topic that you could teach a whole workshop just on this section. So I'm just going to start with some very simple ideas. So with one of the nice things about random forest regressors is that they have a built-in method for assessing the importance of your features. so a random forest regressor has something called feature importances. And so here I'm going to access these feature importances and then sort them in ascending order. So these numbers are giving us a measure of how important a feature is in the overall prediction made by the random forest model. So what we see is that the three most important features are actually median income, whether the house is inland or not, and then the population per household. So that's some measure of kind of population density. And then after that, there's kind of a significant drop down in the feature importance, and you get a whole bunch of features that have relatively low values of feature importance. So what's the takeaway from this? So one thing that you could try doing is say, well, these other four, other than inland, near ocean, near bay, less than an hour from the ocean, and island, all have relatively low feature importance. So the first thing that I would probably do in this case is go back to my feature engineering and my categorical data or categorical pipeline. And instead of doing one-hot encoding for the ocean proximity category, I would create a single binary variable that takes a value of 1 if the training observation has inland as ocean proximity and 0 otherwise. And so this would basically, instead of having these fine-grained distinctions between, whether it's near the ocean or the bay or less than an hour on the ocean or an island, it's basically, is it near the coast or not? And that variable might, or that single variable will reduce the number of features in your data set, which will speed up computations perhaps substantially for some machine learning algorithms, but also might give you might give models like random forest a better split, a better variable that they can split on when creating these decision trees. So there's a question about how feature importance is calculated. So I don't want to go into the details of exactly how it's calculated. So you can look in the, there's a link further up in the notebook to the documentation for Scikit-Learn, and you can read in there. It's not related to the correlation coefficient. It's a fundamentally different idea of measuring feature importance. But you should look in the documentation if you want more details about how it's actually calculated. Okay. So the next thing to do is let's actually compute the prediction errors on the training data. So we can get the true value for the target and then the predicted value for our target by calling the predict method on our best estimator. And then we can compute the prediction errors. And here I'm just going to stick this last line basically creates a prediction errors variable and adds it to our training data set. So now this gives us a data set that has our features, our training features, but as well as our prediction errors. And we can use this for plotting and stuff like that. So first thing we might want to do is actually just make a box plot of our prediction errors. And you can see that our prediction errors some of these errors are huge. So there is one training sample for which the prediction error is on the same order of magnitude as the cost of the house. So there are some values for which a positive prediction error, it means that the model is under predicting housing price, because the prediction error is defined to be the true value minus the predicted value. So if this is positive, then that means the predicted value is less than the true value. So these are all examples of wild under predictions of the house values. And then these down here are examples of wild over predictions of the house values. So one of the things that you could do is say, okay, well, let's take a look at some of these outliers, some of the training samples that for which the model generates these wild predictions, and try to see if we can spot something that is odd. So here, this basically is showing us the values that have the 5 highest values for prediction error, and then the 5 lowest value. And the 5 most positive, so the ones where the 5 census block groups for which the houses are most underpredicted, and then the next group down here are the 5 houses that are most overpredicted by the model. And so you can maybe look through here and try to find some idea of what might be common amongst these models that are these training samples where the model is performing poorly. I was looking through this earlier myself, trying to spot something, and nothing was jumping out at me. If I make this maybe 10, and we could see more observations. So a lot of the population per household. So remember, this is the standardized mean zero unit standard deviation data. So negative values of population per household, for example, indicates that these are census block groups that have lower population per household than average, because they're negative. So, maybe the models are systematically under predicting housing prices for areas that have lower population density than average. Although some of these are quite close to zero, so they're so actually maybe the story is that that's not doing a good job, that maybe the model's predictions are getting driven by extreme values of, say, population density. So maybe one thing to do would be to go back to your original data and ask, like, are there wild outliers in the original data that we should probably just exclude from the analysis to begin with? Because the model is, our criteria, root mean squared error, is going to place a lot of weight on any very large prediction errors. It's going to try to reduce those as much as possible. So maybe maybe the model is spending too much time focused on trying to minimize the prediction error for training samples that are real outliers along one dimension or another. So we can look at, so here's a way to plot the prediction errors by latitude and longitude. So here, I'm plotting the color of the dot corresponds to the prediction error. The prediction error as measured in tens of thousands of US dollars. So places where the model is under predicting, so you can see there's a lot of yellow, there's some yellowish dots here. So this is near, if you know your California geography, so this is near a big lake called Lake Tahoe, where there's lots of really high-priced houses, because they tend to be vacation homes for people who live elsewhere in the United States, or live in like Los Angeles or San Francisco, and they have a second home up in the mountains near Lake Tahoe. And the model is systematically under predicting the prices of these homes. So that's an example of how maybe some better domain knowledge about California geography might be able to construct a feature which would help us do better in these predicting these Lake Tahoe homes. Also, you can kind of see some yellowish here. So this is near San Francisco, or maybe just south of San Francisco. And so this is like Silicon Valley, Bay Area. And then also there's yellow underneath this green and down around Los Angeles and San Diego. So maybe the model is, it looks like it's systematically under predicting home values in urban areas as well. So that might be one hint of where we could go and look for either more time spent with feature engineering to try to better capture a feature that will be useful for predicting home prices in urban areas. So if you wanted to look at how prediction errors varied with an important feature like median income, so here I've just made a scatter plot of median income along the horizontal axis and then the prediction error along the vertical axis. And you could try to do some analysis of this pattern to try to see if there's any obvious way in which prediction errors are varying with median income, because that might indicate a tweak that you can make to your model to improve its predictive accuracy. Okay, so I just wanted to give you kind of a flavor of some approaches that you might be able to use to analyze the errors of your model. So there's a question about, should we include lake with ocean proximity to water? So that's a very good observation. So if you went back, one thing to do would be to identify these census block groups, then go back and look at the data and see whether they were coded as what they were coded as. Maybe they're coded as inland, but they're not really inland. They're actually near a body of water. And there's a lot of reason to think that proximity to water is strongly predictive of housing prices. So going back and taking the various categories of proximity to water versus inland, reducing that down to proximity to water or not, but then making sure that these Lake Tahoe census block groups are properly coded as having proximity to water. So that would be a great example of feature engineering, where we've done one pass through our modeling pipeline. We've got some results. Now we're going to go back and start over with feature engineering and do the whole process again. So I think this kind of proximity to water variable would be the best way to try to immediately improve the model. Okay, so there's a question about, well, what about including a technique like PCA in the feature engineering step? PCA is a dimensionality reduction technique that is typically used to take a very large number of features. Like if you have thousands of features and you wanted to pre-process that down to a smaller number of features that capture a lot of variation in the data. Normally with a data set of this size, PCA is not something that I would start with initially, but there's no reason that you couldn't try it and see. And if you wanted to do that, normally what you would do is you would introduce something like PCA in your pre-processing pipeline. So if you would go all the way back up here, and then introduce PCA either here. So if you wanted to introduce something here, it would be like decomp. So we'll just call it maybe PCA. And then there is actually, it's a different package. It's in decomposition PCA. Composition. And then this would basically add a principal component decomposition, and then you could add, there's some hyperparameters with PCA that you can tune, and then you could just re-estimate the whole thing, and then you have included PCA in your step. So is there an automated way in Scikit-Learn to discard non-predictive inputs such as total number of bedrooms? So there are some, I don't know of any automated way to do it. I think the way that I might, well, actually, let's see. So Scikit-Learn, there's a package called feature selection, which I'm not as familiar with. So I would say that the answer to that question would be to start here. So on this feature selection package, it provides some methods for, but I think this is going to actually be more, I think, but you have to dig into this to find out if this will answer your problem or not. But this might be more filtering out features ahead of time that look like they're not going to be very good based on various criteria. And what you're talking about is more like analyzing the output of the model and then dropping features that don't seem to be important and then going back and refitting again. And I think that you can do that, but you might have to write your own kind of loop to try that, where you would fit a model and then say identify. If you're doing a random forest model, you could say, okay, well, fit a model, calculate the feature importances, then identify features that have importance higher than some threshold, then drop everything else, and then start again from the top. So that kind of logic you could definitely express in a for loop, but I don't know of anything that, I don't know anything off the top of my head that would automate that process further. But it does kind of feel like the type of thing that somebody might have written a package to do. So it'd be worth Googling around and trying to find out. Okay, so where were we? Okay, so evaluating your system on the test data set. So this is going to be really quick because we have encapsulated our feature engineering in a function, our data set cleaning in a function, and we have our pre-processing pipeline that has memorized all the values of the hyperparameters we use to pre-process the training data set, and we'll apply them to transform the testing data set. So first we load the testing data set. Then we do feature engineering on the testing data set, cleaning the testing data set. We split the data set into testing features and testing target. And then we take the pre-processing pipeline and we call the transform method, not the fit transform method, but just the transform method. Because we want to transform the testing features, applying the same values of medians and the same rescaling means and standard deviations that were computed on the training data. doing that gives you the best estimate of out of sample performance. So we do that, and then we're going to do we're going to take our randomized search cross validator, the best estimator, and then we're going to predict using these pre-processing testing features to get the predictions. And then we're going to compute our root mean squared error. And so we get 43,484. So now there are two numbers that you need to compare your test error with. One is the training error. So the fact that our test error is similar to the training error tells us that our model is not generalizing quite well to the new test data. It's not overfitting. So if our model had been overfitting, we would have gotten a much higher value for the root mean squared error on the test data set than we got on the training data set. So that's one comparison that you need to make. The next comparison that you need to make is to the root mean squared error on the test data of either the existing model, or the existing solution, whatever that might be, if it exists, or to some other model. So normally I would carry through to this stage maybe 2, at most 3 models that I would basically, candidate models that I would invest a lot of hyperparameter tuning on to have 2 or 3 models that I think are worthy of putting into production or worthy as serving as the solution to my machine learning problem. And then I would test all of them against the testing data set. And then the one that had the best or the lowest root mean squared error on the testing data set would be the one that I would go with. A point estimate of the test error is okay, but you can generally do a little bit better by kind of just doing a quick confidence interval for your testing data. So if you produce a confidence interval, then this gives you kind of under a certain set of statistical assumptions, a roughly 95% confidence interval for this point estimate of the root mean squared error on the test set. So if the root mean squared error for the current model, the current solution, whatever that might be for our house price prediction, if it fell within this confidence interval, then you might say, okay, well, our model is not significantly better than the current approach. But if the current approach had a root mean squared error that was well outside of this confidence interval, then you would have some indication that your new solution is significantly better than the current solution. There's a caveat here about if you do maybe too much hyperparameter tuning can be a bad thing, because the more hyperparameter tuning you're doing, the more likely you are to maybe overfit to your training and validation data sets. So that's another reason to kind of, you can't just do an infinite amount of hyperparameter tuning and expect to eventually find an amazing solution. Typically, in my experience, hyperparameter tuning gives you marginal improvements, and major improvements come from either getting more data, better feature engineering, or switching machine learning algorithms. So that's it. So I think that's, we've covered a lot of ground, from last week where we talked about, how to get data, how to automate the process of getting data, how to do basic data analysis and analyzing the data, getting a feel for what relationships in the data might be important. And then we spent a lot of time the first half of today on data pre-processing and cleaning and talking about the importance of that and feature engineering. And then the last half of today was focused on the mechanics of learning how to apply the Scikit-Learn API to to fit machine learning models and then do parameter tuning. Okay, so we have about 30 minutes left. The rest of the day is going to be Q&A, so I'll hang out as long as there are questions coming in chat or otherwise. But let's see what we have here. So so I'm just going to stop sharing my screen for now. So there's a question in chat. So can machine learning be unsupervised with no labels? Yeah, absolutely. So there is a whole slew of algorithms in Scikit-Learn for doing unsupervised machine learning. And these are going to be like clustering algorithms and things like this. Here we focused on a supervised learning problem, but there are definitely many interesting and well-defined unsupervised machine learning problems. Any other questions? So there's a question in chat. So did you try running deep learning on today's housing data, and what results do you get? And if you did not try it, what results would you expect? So I did not try to run a deep neural network on this data set. I would not expect deep learning to do significantly better than what you would get with classic machine learning approaches on these kinds of data sets. Where deep learning, I think, really can perform well are, well, certainly it's state of the art in computer vision and sequence analysis. So time series, like if you've got complicated time series analysis that you're doing, so like deep learning approaches would be something that I would very quickly kind of consider in that kind of a situation. But for tabular data like this, that is relatively small, these kinds of classical machine learning approaches will do as good, if not better. And I would guess that if deep learning was able to improve upon the solution that you would find with these kind of classic machine learning approaches, then the additional implementation costs and overhead of creating a deep learning pipeline would outweigh the marginal benefits and improvement that I would expect on a problem like this. Good reference for machine learning theory. Wow. So Mohammed, I wish I had a better answer to this question. So I don't have a great reference off the top of my head for machine learning theory. So that's something that I should have a good answer for. So I'll make a note about that and maybe try to put some references and links on the video. When it goes up on the YouTube channel, there will be links below the video to different reference materials and things that I've mentioned here. So I'll try to put a link for a good reference for machine learning theory. I just can't think of one off the top of my head. Okay, another question. So if you do not have a lot of imaging data, can I still use deep learning? Oh, yeah, of course. I mean, you can use okay, so how to phrase it? So I'm not trying to scare you off of deep learning and applying deep learning in your problem. I'm trying to relay my experience that in many cases, the investment in deep learning is often not worth the cost and the additional complexity. Scikit-Learn and Rapids for GPU accelerated classic machine learning pipelines have really made the construction of a machine learning pipeline easy to create and test. There's a lot of the a lot of additional complexity and overhead with deep learning models, and you just need to, you should be familiar with the ideas of deep learning for sure, and try to have a good understanding of when you think deep learning might be a good solution for your problem. So I mean, the areas where deep learning is clearly the state of the art, and you need to know and understand deep learning, is in computer vision, natural language processing, and reinforcement learning. Those are the three areas in which I would say deep learning would be the obvious place to start if I needed to build a high performance application in those domains. I probably wouldn't spend any time with classic machine learning techniques. But you also need a lot of data with those models. So it also depends to some degree on the amount of data that you have available. So computer vision and natural language processing are areas in which data sets are massive. So image data sets, text data sets. I mean, these models are state-of-the-art models are being trained on like all the English language text in the entire internet, or other similarly large data sets for other languages. You know, reinforcement learning, data sets are generated by interacting with an environment. So you have almost a never-ending supply of training data that you can create via simulation. So in those domains, it's probably not surprising that deep learning has become so dominant, is because there's a huge amount of data available for training. In other applications, data might be much more limited, in which case you're unlikely to be able to train a deep learning model that's not just going to overfit the minimal amount of data that you have available. Okay, any other questions? Best ways to deploy trained models. So give me a moment. So let me just pull up my teaching notes and see if right. So deploying trained models is not something that I have a lot of experience doing myself. Most of the applications and clients that I work with at Calus are more on the research, and the deployment stage is not something that 99% of their models ever get to. So what I can say about deploying models is many of the major public cloud providers, so Google, Amazon, and Microsoft, have invested a lot in improving infrastructure in this area. So if you have a trained model, they have APIs and tools that allow you to effectively embed that model in a web application. And what this means is that at some point in your web application, like if you're embedding a Scikit-Learn model, then at some point into a web application, at some point a user would interact with your website in a way that would generate data that would be passed into the predict method of your Scikit-Learn model, which would return a prediction, which would then go back to the user, and then the user would do something with that information. So that's what it means to deploy a model. It's like taking I guess another comment would be, so remember when I showed you how to use joblib to serialize the model file to disk? That's really important for deploying a model, because you take that file, that single file which controls the model, you embed that in a web application. So the web application has a little bit of Python scikit-learn code in it, but it basically just loads the scikit-learn model that you serialized and then takes the data from the user, puts it into the predict method, and then returns the result. So it's basically like a trained model is like a function that takes input from the user and returns a result. And then you embed that into a web application where the user's input is coming from mouse clicks or entering information into a form or copying and pasting text into a text box if it was like some kind of like Google Translate, for example. And is it possible to turn them into executable files and embed them into other Windows programs? Yes, but it's not something that I have experience doing. But what you would do is, so yes, you can take because at the end of the day, a scikit-learn model is just going to be a little Python program, and you can embed Python programs in any kind of executable files. But at this point, like these kinds of questions, it really depends on the exact details. So like if you have a problem that it requires embedding a Python program into an executable file like that, reach out to us and at the Viz Lab, and we can see if it's something that we can advise you on. And if we can't help you, we can probably point you in a direction that would be useful. Okay, any other questions? Oh, good reference. I don't have, so the question is, do you know a good reference to create web services around these trained models that can be called from Windows or a mobile app? I don't. I will do a quick search and try to add links on the YouTube channel on deploying models. But where I will probably start, if you want to get working on this now, is on the like Google Cloud Platform documentation, Amazon Web Services documentation on deploying machine learning models. They will have a lot of resources and services, because that's where they make a lot of their money, is by providing the infrastructure to help people both train models on their platform, but then deploy models into production, also running on their platforms. Okay, any other questions? Last chance. Okay. Well, thank you all very much. You are more than welcome to send along any follow-up questions you have via email. You can either email me directly at Calst, or you can reach out to the Viz Lab, and those questions will be forwarded along to me. Thank you very much for spending your 2 Thursday afternoons the past couple of weeks with me learning machine learning with Scikit-Learn. I hope you got a lot out of these workshops, and I hope you were able to find a way to use Python and Scikit-Learn and all the other tools that we've talked about in your own research or work. And I will put my email. I'll make sure that you have my contact details. So they should be. I'll be sending. Oh, reminds me. So I'll be sending out an email probably on Sunday with a link to the uploaded videos on our YouTube channel. The last week's episode is already uploaded. This week I will upload probably this weekend or on Sunday. And there will be a link to a feedback form for you to provide some feedback about this workshop, these 2 workshops, so we can get some ideas on how we might improve them in the future. So I'd appreciate if you take the time to fill out that feedback form. But my contact details will come along with all of those with those emails. Okay, well, goodbye everyone, and thanks for joining in.